Next speaker is Marina Marinkovic, who will tell us about quantum many-body scars and 3D gauge.
Thanks a lot, Igor. I'm going to shift gears a little bit with respect to Larry's talk, except that I'm also interested in real-time dynamics, and but in simpler systems, in 2+1 gauge theories, in Hamiltonian formulation, which was discussed in several talks earlier today. We will use a specific formulation of U1 gauge theory in order to study these states which evade thermalization in a weak way, which evade eigenstate thermalization hypothesis. So lattice gauge theories can be considered once we write them in a specific way, which is equivalent to spin systems. Then we can consider them as also quantum many-body systems. And we know that in quantum systems with many degrees of freedom, we can sometimes find initial states that fail to thermalize or have extremely long thermalization times, and this goes back to the eigenstate thermalization hypothesis. And what we were interested in, so over the recent years, and I'll show you references soon, there have been many situations where, so there have been many gauge theories in which these quantum many-body scars have been constructed or found empirically, and but mainly in lower dimensions. And we are interested now in a 2+1 dimensional theory, as the title said, and we're also interested in the conditions under which the eigenstate thermalization hypothesis can be evaded, and where we can get weak or strong ergodicity breaking in gauge theories. Now, as I mentioned already, quantum many-body scars have been found in simple gauge and fermionic theories. When I say simple, I mean lower dimensional theories, mainly 1+1, the Schwinger model that has been discussed, or equivalence of U1 theory in 1+1 dimensions. And more recently, there have been a few studies, including the one that I'm going to discuss today, done together with my PhD and a postdoc, with doctoral student Thea Bude and a postdoc in my group, Joao Pinto Barros, who is talking about the same work currently, but in Japan, on a parallel workshop on quantum simulations of gauge theories. So, in these recent works on quantum many-body scars, since this is a real-time dynamics problem, as we've heard again in the earlier talk today by Ross, we can probe these systems numerically only for small volumes, because we need to exactly diagonalize the Hamiltonian, so the Monte Carlo methods, which work very well for Euclidean lattice gauge theories for static quantities or zero chemical potential, have severe sign problems if we want to study real-time dynamics. So what we try to do here is to extend this to larger volumes, this study, and also to construct a tool which would allow us to probe these quantum many-body scars in the continuum theory, potentially. And I'll come to that in a moment. So,
yes. What does it mean, many-body scars? The last word. What does the last word mean? Scar.
Shram.
I understand it's shram, but
Just once, like, what's this terminology?
Yeah, I don't understand. I know the translation of the word scars in different languages, but in terms of many-body systems, what does it mean?
You have many bodies, you damage them, and they attempt to heal.
No.
I will define it. This talk will probably answer.
I will define it in a moment, but let's say that you're interested in anomalous thermalization properties. So if you have a many-body quantum case, you prepare this quantum state and let the system thermalize, and then come back and measure the system. Quantum eigenstate thermalization hypothesis tells you that for local observables in quantum many-body systems, you will converge to same value independent of initial conditions. And in these scarred states, I attempted to illustrate it here, are some special initial conditions that avoid thermalization. So if you run over a long time, your initial state will fail to thermalize. And this is really well known in condensed matter, in many-body systems, and again, also they are studying larger system problematics due to severe sign problems of this real-time dynamics. And these states have also been detected experimentally in analog quantum simulations with Rydberg atoms a couple of years ago, and the interest in these states was reignited. So this was the case for U1 theory, so actually PXP model, which can be shown to be identical to the scars that have been found there, that they correspond to the Schwinger model. So 1+1 U1 scars. And we want to study these scars analytically, if possible, in order to provide some benchmarks potentially also for quantum simulations, which might be able to detect the scars also in higher dimensional gauge theories. Yes, please.
What is the status of the question of large times? I remember it was disputed recently. What happens when you evolve for sufficient time? Does it always thermalize eventually or not?
The scar, does it thermalize? No, I mean...
Eventually, like a very long time.
I think so. So this is theoretically, you cannot check that for a very large time. But I mean, we will call the scars, and as you will see in a moment, so we can measure, for example, the entropy of these states, and we can show that. So it's not only that it doesn't thermalize. The fact that it doesn't thermalize is just one of the indications, but you can see that these scars are some low spectrum states, so mid-spectrum states with low entropy, significantly lower entropy than the other states. So you would not then expect them to thermalize. You may see in the experiment the signatures of thermalization, but just because you cannot fully control this time evolution.
Yes.
Not qualified.
I thought that asymptotically any state thermalized.
She says no.
This is finite degrees of
There are
freedom.
some exactly models
Not
where
in the
they're
limit
exactly
on the
decoupled. But
and the final degree of
Exactly. So I mean, I'm not sure which theory you're exactly referring to. I mean, it can be the case that you haven't resolved the symmetries of your system properly, and the state that is indicated that looks like a scar in the beginning may not be a true quantum many-body scar. But this is the reason why we actually need to work with simple enough theories where we can resolve these states analytically, and this is something that we managed to do here for U1 in 2+1 dimensions, to really identify how many scars do we expect to have for certain finite size lattices, and I'll show you this in a moment, but we can come back to that. So as I said already, so those are some mid-spectrum usually, so high energy, but not all the way at the top of the spectrum, but mid-spectrum states, which are, so the gap between the states is exponentially small, and the intuition about this eigenstate thermalization hypothesis is that if we add some small perturbations to the Hamiltonian, these small perturbations will mix many of these mid-spectrum states, and they will end up being highly entangled. And if you look at the entanglement entropy for, or also Shannon entropy for these states, one really sees that there is high entanglement of these states in the middle of the spectrum. And the eigenstate thermalization hypothesis is quite, of course, old result, but still a hypothesis. So we expect the local observables to thermalize due to this intuition that I tried to illustrate, and the hypothesis itself bounds the fluctuations about the mean, which are exponentially suppressed, function of the average of the energies of the two states in the sum, and multiplied by some continuous function or smooth function over random, real, or complex variable. And now the ergodic hypothesis is another way to to rephrase this eigenstate thermalization hypothesis, basically tells us that our Hilbert space of this quantum many-body system will be a single fragment. And if we have a breaking of this eigenstate thermalization hypothesis, we would have fragmentation in our Hilbert space. And now it depends whether this comes, if we have exponentially many fragments, so this is a breaking of eigenstate thermalization hypothesis, which corresponds either to disordered systems, to chaotic systems. We also wouldn't expect, if we have an integrable model, then this eigenstate thermalization hypothesis would be broken as well. And the largest fragment of the Hilbert space divided by the total number of fragments would be exponentially suppressed. And these quantum many-body scars, so once again, those are states which corresponds to the weak breaking of this eigenstate thermalization hypothesis, which means that we have many, but not exponentially large amount of high energy states. And so this largest fragment divided by the total number of fragments goes to 1 as we increase the volume of the system when it's weakly broken. And then these special states are still part of the mid part of the spectrum, the quantum many-body scars, and they don't mix significantly with other states. And this is something that we can also, once we find these quantum many-body scars, we can also demonstrate that they are a superposition of a finite number of the elements of the eigenstates, the finite number of the basis elements of the Hamiltonian, while these normal or standard mid-spectrum states, which are highly entangled, are a superposition of a large number of elements of the basis. And as I mentioned already, so another signature of this anomalous mid-spectrum states, so if you compute, you can use the entanglement entropy or also Shannon entropy. I will focus on this one in this talk, but in the paper that I showed, we compute both for each system that we study. And so you can compute if you split the system into two, we always do it into two identical. I mean, one can optionally do this. So we split our lattice, two-dimensional space-time lattice. We're interested in a time evolution, so this will be the third dimension. So our Hamiltonian is two-dimensional. We split the system into two identical parts. We precisely define whether this line corresponds to the left or to the right system, and then compute the trace with respect to one of these two halves. And then the standard distribution of the entanglement entropy, this bifurcated entanglement entropy, has this arc form. And if we would find quantum many-body scars, we will compute the same quantity for them, and you will see that they have significantly lower entanglement entropy. So this is just a sketch, and I'll show you the actual data in a moment. So now these quantum many-body scars, as I mentioned already, have been observed experimentally with Rydberg atoms. There has been an extensive activity in studying 1+1 and 1+1 dimensional gauge theories for a variety of spins. I'll define what I call spin in a moment, but it was mentioned already in earlier talks. So we have to make our Hilbert space per link finite if we want to do, for example, quantum simulations of these systems. And there have been a few predictions for quantum scars also for spin 1/2 Hamiltonians, which correspond to U1 gauge theory. So in this talk, we are focusing on 2+1 systems, and we've managed to construct these quantum scars for arbitrary spin. And as we will see in a moment, we need to take the limit of infinite spin in order to recover the continuous gauge symmetry that we've initially represented with this finite Hilbert space per link. So you've seen this Hamiltonian already earlier today. There is a kinetic term, and which involves Plaquette operators, and then there is also a potential energy term, which is in electric field basis, looks like this for 2+1 dimensional U1 gauge theory. And this comes from the quantum link model formulation of gauge theories proposed for condensed matter systems already in the 80s and then in the 90s by Uwe and Wiese and Shailesh Chandrasekhar and Rich Brower as well worked on this proposal where the electric, so these plaquettes operators consist of electric fields, and we have the unitary raising operator which acts, so the U fields act like a raising operator on the electric field states on each link. Now, this is known as quantum link models, but what we will be working with, even though I'll show you also one example of quantum link models for spin 1, the formulation in which we managed to generalize this to an infinite number of spins corresponds to truncated link models. So this is a slight modification of this raising operator, which looks almost like a unitary operator, except that at the end of the lattice, we artificially chop the spin, so it's not a it's a unitary operator on the bulk of the lattice. And this goes under the name truncated link models, was proposed some more than 10 years ago. There was some discussion over the years, but I think this has been settled in the meantime that both truncated and quantum link models converge to the correct theory. And we've been able to correct continuous gauge group, and we've been able to check this in 1+1 dimensions. The reason why this hasn't been checked in higher dimensions again is that we need to perform exact diagonalization for large or quantum simulations for large values of spin, which is currently not feasible with the methods that we have at the moment. So, so this truncated Hamiltonian, again, we have this unitary looking raising operator, but and we also truncate our fields in order to have a finite dimensional Hamiltonian per each link. And then we need to take the limit of S to infinity. In practice, it's sufficient that S is large enough. But as I said, in 2+1 dimensional gauge theories, it's hard to simulate even with quantum simulations and also with exact diagonalization for large values of S. So here we try to, instead of performing a numerical simulation, to construct these quantum many-body scar states analytically for arbitrary S, and then check for small values of spin numerically with exact diagonalization that these states that we constructed are indeed scar states in our system. And I'll also refer you to, so this is quantum link model formulation, and there are also alternative formulations where you need to pay attention also to the potentially fixing the gauge in the theory and so on. Now, I didn't mention, but also as in previous works, we focus on the zero, on the sector of the Hilbert space which satisfies the Gauss law. So in Hamiltonian formulation, we also have additionally to impose this constraint. And now there are several symmetries which one has to take into account when constructing these charge states. There's this usual lattice translation and lattice rotations with respect to x and y axis that you're used to already. I want to stress here another symmetry. Also, Martin has shown you a few of these interesting operators that we can compute in Hamiltonian formulation. So I'll stress here this charge conjugation operator, which is a product of links on every second line. So every second, let's say if we sum over x, so every other x, and then product of links along all of y-axis. And the other way around, we can also define it as for every second y coordinate, so here, here, and here, and then a product of links along the x-axis. And So this is a symmetry of the kinetic part of the Hamiltonian. So if kappa is equal to 0 in the previous definition of the quantum length Hamiltonian, then this charge operator commutes with the Hamiltonian. And from this property of this charge, we can see that so one gets an infinite, so exponentially large number of zero modes. And if we define this type of operator in non-integrable spin chains, and this has been shown for spin models some years ago by Schlechter and Yadakola, and we use this property in order to construct the zero modes of our theory. So these are the zero modes of the kinetic part of the Hamiltonian, and the fact that we have this C charge which protects the zero mode by an index theorem makes sure that we have an infinite, that we have an exponentially large number of zero modes in spin systems. But before we construct these zero modes, we have to make sure that the system is actually non-integrable, such that so we didn't do it in this order when we were constructing these states, but once we found the quantum many-body scars, then we had to make sure that our theory is non-integrable, which we expect also for quantum link models, but we have to make sure that this also holds for the small lattices in which we've actually explicitly constructed these states. And that we can do if we resolve all the symmetries of our Hamiltonian for a particular choice of the lattice. So we will be working a lot with these ladder-like lattices. It's a 2+1 two-dimensional system, so 2+1 dimensional 2+1 dimensional theory. Then, if we evolve this in time, but also convenient for experimentalists to realize, since connecting these plaquettes is easier than actually building fully two-dimensional lattice. And in this particular system, and also in several other systems that we studied in the paper, we can check that, so since we work with open boundary conditions here, then the translation is broken symmetry, and the only symmetry that we have to resolve is the reflection with respect to the y axis here. And once we resolve and enumerate these two sectors as a negative and a positive symmetry sector, then we can compute the level spacing distribution as defined here. And as you know, in integrable systems, we expect to get a Poisson distribution. And here we see clearly that we actually follow Gaussian orthogonal ensemble distribution, which demonstrates once again that our system is not integrable, and that these scar states that we're going to construct are indeed the states for the non-integrable system which evade eigenstate normalization hypothesis. And now we take the zero modes of the kinetic Hamiltonian and construct them by hand for a two-plaquette system. So this, I'm not going to go into the details how we do that. Had to sit a little bit and then try all combinations of the zero modes. So one can construct several zero modes on this small system, and then find the one which has the lowest entropy. And then we will see that due to the charge conjugation that I mentioned previously, we can simply apply the charge conjugation, and if we found one of these low entropy states, we will immediately find another state which is charge conjugate to the first one of these low entropy states. And the nice property, so these are zero modes of the kinetic part of the Hamiltonian, but the nice property of these states is that we can put them together. So we can tensor them, and in a way actually which was mentioned in the previous talk already, and then we can construct zero modes zero modes of the kinetic part of the Hamiltonian for larger lattices, which also have the lowest entropy possible. And then we can continue this tiling procedure in 2 dimensions in an arbitrary way. So once we have found a lowest entropy state for the two plaquettes, then we can tile them in several different ways together and construct zero modes for larger lattices. And then So we can check that this is indeed the zero mode of the kinetic part of the Hamiltonian. Now we've canceled the potential part. We need to then now break the index theorem by now adding the potential part. And we will construct the potential part of the Hamiltonian such that these states are still eigenstates of that full Hamiltonian with a non-zero potential part. And so this does not allow us to construct zero modes for all possible potentials, but we have to construct, so there is some engineering in this process of constructing potentials for which this is indeed an eigenstate. And so these stylings of duplicate states are eigenstates of a large family of potentials. One of them is the one listed here. So recall in the quantum link models you have the electric field squared. And here there is just a single electric field, horizontal links, the product of horizontal links, or the sum of horizontal links on the top row here. And you see that, so from the styling procedure, we know that we have to get exactly 4 scars because we can tile them starting from the first lattice or shift by 1. And then we have also the charge parity state, 2 additional state. And if we perform the diagonalization for this Hamiltonian, we exactly get these 4 states which have significantly lower entropy than the mid part of the spectrum, which corresponds to non-scarred states. And then we've repeated this procedure for many different lattices, also for different spins. So for spin 1, for spin 2, and in the paper we also give the procedure to construct this type of scarred state for an arbitrary spin in the truncated link models. So due to the property of the potential, which does not have this square. So for quantum link models, we were able to do it for spin 1. But also on larger lattices, so not only on the larger lattices, but for truncated link models, we could do it for an arbitrary spin. So this is a truncated link model, and you see clearly that there are these scar states which have low entropy.
But the ground state has even lower. The ground state has even lower entropy.
Here.
The ground and the highest state.
Exactly. So, but this is not
scars.
They're not scars, yes, because the scars are these mid-spectrum states, which
not necessarily.
Well, the ground state is the eigenstate of the Hamiltonian. So
they're all eigenstates. Yeah,
they're all eigenstates
there are
of the
models
kinetic.
where the ground state is also a scar, but.
Okay, I'll have a look at this. I'm not aware of it, but so they're all eigenstates of the kinetic, the kinetic part of the Hamiltonian. But this initial state is a combination of several different eigenstates of the full Hamiltonian. Because if you start with an eigenstate, you will of course never thermalize. So in that sense, if it's purely an eigenstate of the full Hamiltonian, then it won't thermalize, but it wouldn't be called a scar.
So in your 6x2 data, it looks like your scarred states, so to speak, are just mixed up with what you're calling non-scarred states. They don't look that exceptional.
Yeah.
Exactly. Yes. Well,
I think most people would not accept the scars.
Sorry?
Most people would not accept the scars.
Yes, so this may be also, so we're still looking into this, it may be a property from the size of the volume which we have. As we go to scale this up in larger volumes, it will be interesting to look into this. And those also correspond to quantum link models. So, but for the truncated link models, there is a much more clear separation and also a formula to construct these scars.
You understand in the truncated, there's another 5 states above that also seem much lower than the rest, these ones. Do you know what those are?
We have not looked into them. It may be that we are not constructing all possible. Right. So this is a procedure to construct a large family of scarred states analytically for large S. But whether we're picking up all possible scarred states, that we would need to look into. But it's a bit difficult to reconstruct it from the spectrum.
It seems like there's sort
directly.
of different levels of scarredness or something. I don't know.
There are all kinds of such
There-
things.
Exactly. There are also different types of scars, so we did not. So this again gives us a procedure to construct them for an arbitrary spin, which we find interesting because we would then be able to study them in the continuum limit as we take the limit of S to infinity. But just to demonstrate that these are indeed scars, we've done the numerical simulations. And I'll now move to the conclusion. I see that my time is almost up. So we've are interested in this real-time dynamics, as several other talks earlier today. There are initial value problems in quantum field theory that may be answered by this explicit construction of quantum many-body scars in gauge theories. And then we've seen that if we have zero modes of the kinetic part of the Hamiltonian, that it allows us to construct quantum many-body scars for arbitrary spin in 2+1 dimensions. Now, there are some questions which we still want to answer. For example, can this be generalized for other models? There has recently been, actually the same day as our paper came out, we coordinated also submission with colleagues from Munich who've used tensor network approach, not to construct these modes explicitly, but to study them in 2+1 dimensional theories with matter, with bosons and fermions. And they have interesting observation that if dynamical bosonic matter is added to this theory, that the scars are still there, but if dynamical fermionic matter is added, that the scars are not there anymore. And this is something that we will try also to study with this explicit analytic construction, but requires some work to include the fermions as well in this construction. And one of the very interesting questions is whether they're still present in the continuum limit, which this large S constructions now allows us to do. Of course, long-term perspective would be to extend this also to theories beyond U1 and potentially, which would potentially have impact for heavy ion collisions in QCD and so on. All right, there is a large body of literature for quantum simulations of gauge theories more recently that I didn't get to cover here, but I wanted to share this with you. Also, more recently, there has been string breaking in 1+1 and 2+1 dimensional theories that has been studied with quantum simulations. And in my group, we're also working on quantum simulations of U1 theory in 1+1 dimensions, and we've recently developed a method for adiabatic state preparation, but this is all in lower dimensions than what we've managed to address here analytically. So I thank you for your attention.
Thanks so much for the nice talk. Did you try to, usually for these scars in quasi one-dimensional systems, the entanglement entropy grows like log L, log of the number of sites. Did you try to check if there is logarithmic growth?
Of the entanglement entropy?
Yeah, it grows like log L. That's sort of a signature of a true scar.
True scars, yes. So we get that. Actually, I'm not sure whether I might have included this. It's one of the backup slides. Okay, so no, so this is just the observable. But yes, we can. One can check that.
Yeah, it's like a typical state will be L, and this one will be log L.
Yes.
That's
Yeah.
something. Any more questions? Okay, let's thank Marina again.